Thank you. It's a pleasure to be back at Q2B. And I'd actually like to build a little bit on the talk by Julian van Velsen this morning, if anybody saw his talk, which really sort of talked a little bit about the end-to-end process of getting value from quantum computing. So first of all, looking with organizations, with end users at where that value might come from. Then beginning to look at use cases, and then really beginning to go deep into tackling those problems. And actually, in contrast with some of the work we do, this is really actually a first step. This is early in that journey, this initial project. This is work done with one of our partners, Unilever, a major player in the consumer product space. And while we, as an organization, work extensively on innovation in R&D with clients like Unilever, actually finding where quantum computing may come into to some of their work has been an interesting journey for us. And this is something which I want to talk a little bit about in this presentation. So to just give a bit of an outline as to what to expect, I want to give a little bit of a background and talk a bit about how we've been approaching problems in the chemistry and materials space, and been exploring how we think there could be value by thinking about all of the pieces which come together. And then I want to talk about a specific challenge which is faced, which is hydrolysis of key ingredients, so degradation of ingredients which are actually related to product experience. And actually this is one particular example which is very much a real problem, a real challenge in the consumer products industry. It's something of a toy problem as far as quantum computing is concerned. It's a first step on that journey, but I'll build that out as we get through the talk. So I'll first of all talk a little bit about some of the predictive features that can go into a data-driven approach, focusing on classical methods, and then I'll talk about mapping that in as a sort of example of how pieces can come together in a quantum computational pipeline. And in the last part, I want to talk a little bit about actually where do we see some value coming in this industry and in other industries from methods and overall approaches like this. So this is very much the plan for the next few minutes or so. So let me begin by talking about our pipeline, which I think Julian flashed this slide up this morning for anyone who was in that talk. Our aim is to try and get value around the tipping point scales for quantum computation by framing problems in such a way that we can capture relevant information about chemistry on relevant scales as part of a bigger problem. And one of the key ingredients in that is the use of embeddings, like several people are looking at, so identifying how to focus our energy in terms of the quantum resource on key parts of that problem, for example, binding sites, reaction centers, etc. And then with effective Hamiltonians that come from those embeddings, look at how we can extract key features of those problems. And there are a number of ways in which we have explored to do that. And then capturing some of those features and bringing them into data-driven pipelines. And it may be, and we'll touch on this later, that there are features which come from quantum calculations and which come from other sources, classical calculations, which can feed into that. And that's something that certainly we expect to be the case. Let me give a couple of examples before we dig into this talk. So in previous work that we actually presented in Q2B, our quantum fingerprint, our set of features which are informative, were actually anchored to the idea of Hamiltonian simulation. So we were looking at approaches which naturally scale on quantum hardware, and then asking the question, are they informative about a particular challenge? And we showed that we got some interesting novel clustering of drug molecules through this route. And this was a very nice end-to-end story. In this bit of work, actually, we're going to look towards a different route and look at ground state properties and actually look at whether there are features that can be extracted there which are useful. And this is actually slightly better trodden ground. And so actually, we'll talk through that in this case. But as we see it, there is a whole multitude of opportunities end-to-end to use approaches like this, frameworks like this, where we can get value from quantum resource in future as part of a bigger problem. And just to give one final comment on that, I've spent much of my career working with drug discovery organizations, and this is very much in the spirit of ligand-based drug discovery, where, yes, there is key modeling of a drug molecule, but actually we may infer properties of what it binds to from a data set, and so it combines those two elements together. This sort of naturally mirrors onto the right-hand side of this pipeline, which I've shown here, so just to give a concrete example. But let's talk about consumer products. Oh, I should say very briefly, there are many things we can do. So that's kind of what I was indicating here. Many ways to embed, many kinds of features to extract, and many different kinds of challenges on the right-hand side. So for example, it may be features which constrain a generative model, for example, not just looking at classification or regression challenges. OK, a few words about esters. So esters are responsible for many flavors, aromas in consumer products, and they all take the structure shown on the white box with two R groups, so two alkyl or aryl groups. And here's a sort of table of some examples of those different R groups, and you can see that you can create a range of different flavors, different aromas, which can go into consumer products. So in the design space of a consumer product, when you're creating a formulation, you have quite a lot of different options, and you also have multiple objectives that you're seeking to fulfill in selecting that design. You can see some of these, they have the same, essentially similar flavors or the same flavors, and so there's really real flexibility in how you create that formulation and how you choose your chemistry. One of the challenges is that some of those key ingredients which actually shape the experience of that product can degrade over time, and that's a challenge if this occurs before the end of the shelf life of that particular product. So it's actually quite naturally linked to sustainability, because you would like to have ingredients that give you a suitably long shelf life. And if we take a step back and think even more broadly, actually, we're often after studying degradation of components, for example, in packaging as well, where we want ultimate degradation, but not within the shelf life of the product. So that's a potential challenge here. Now, in this case, we were looking at hydrolysis of esters in acid or base solutions. But when I spoke about some of the extensions and where things get more challenging is if there are catalytic effects due to, for example, enzymes, other mechanisms which are more complex to study. But let's study with this. Let's focus on this first of all, because this is very much today done often as one of many tasks using cheminformatics techniques, QSAR, etc., and see where we get to. So I want to talk a little bit about predictive features from electronic structure. And I said last time our focus in previous work has been focusing on what quantum hardware will do well, and then asking the question, is it useful to a task? And we found some cases where it really, truly is. In this case, we're going to look at cases where we're interested in driving accuracy in some of the features that we can extract from a problem, and that leading to better data-driven models downstream. So one of the first things that the chemistry team applied was just looking at bond lengths, essentially, looking at some of those around the ester group and seeing essentially how predictive those were. And so where electronic structure does come in, of course, we through geometry optimization and ultimately therefore finding those bond lengths. And I should say this is actually gave us our first experience getting to play with Prometheum and exploring how that could accelerate things, and we had a very good experience substituting some of our usual tool set and exploring Prometheum instead. So actually the DFT results I'll show in this section actually come from that. But if we follow this through, these are actually modestly predictive already. So not potentially the toughest problem in the world, but how much better can we do? We then moved on to look at some more involved features. The idea being to create a big feature vector associated with the electronic structure of a problem that we can then plug into a machine learning model, and it will use the features which are most informative. So I think Julian showed a sneak preview of this morning and highlighted that we're looking at bond critical points, so saddle points in the electron density along key bond directions. And there are loads of features that can be associated with that, so the density itself, the position, curvature, ellipticity, etc., and you can produce a whole set of features that go into a downstream model. And this significantly improves things, and actually you see in this case that we're up to out of distribution explained variance nearing around 90%. So this is really pretty good, and it's actually significantly better already than you get with traditional cheminformatics techniques. So it's quite a nice example of actually trying to explore where quantum may play a role and actually learning something about your problem and delivering some value on one of the sort of first stepping stone problems in the first instance. We also then had a look at how the end-to-end quantum pipeline would apply to challenges like this. And one of the things that we looked towards was framing it in terms of embeddings, and then looking at how we would extract those features. And since these are essentially ground state properties, we're looking at simulating variational algorithms for effective embedding Hamiltonians, which are relevant for the core of this problem around the reaction center. And so this is what we did. We applied density matrix embedding theory, naturally associating fragments with the key atomic bonds that are relevant in the problem, so that we could pull out those topological features from each of the bonds and essentially create a single DMET model for each of those. And you can see some examples on the right-hand side. So in this case, the fragment is a set of two atoms in each case, and through the DMET procedure, we find a larger cluster capturing entanglement with the immediate surroundings. And then we apply, essentially in this case, look at VQE to get to the solution, look at the same properties. And it's not completely surprising that we're not going to do any better on a challenge like this. In fact, the solutions that we get for the features are almost identical within a very tiny percentage difference. Actually, one of the biggest things that drives performance in this problem, of course, are things like the basis set, etc., and that's not unexpected. But it shows how a problem like this can work end-to-end with a goal of being able to move to tougher chemistries where we want to expand that active space that we're looking at to extract key properties from. So this gives us another route to explore. We did ask the question whether looking at Hamiltonian simulation could add anything to this problem. So we'd seen in other challenges that actually looking at Hamiltonian simulation and taking measurements of 1, 2 body observables at specific time points and creating a feature vector from them when prepared from outside of the ground state. So for example, in a Hartree-Fock ground state, we found that predictive. And so we looked at that here and looked at sort of evolution of some of those key features to see what it added to the challenge in this case. And the answer is that actually those dynamics that you generate using the embedding model do correlate with, for example, the hydrolysis rates, but they don't particularly add any additional features. So actually you begin to quite quickly overfit your machine learning models, at least on a data set of the kind of size that we're talking about here, where we're talking about a few tens of molecules, potentially up to sort of 80 molecules in an example data set. So we still think it could be promising, but again, this is a first problem. It's one of the lower hanging fruit, and therefore, given the data set size, there's a little bit less scope to throw in every single feature that we could calculate and put it into the mix. Okay, despite that, we do think there are various situations where these ideas could be genuinely of value going forward. So it's not really a surprise that single reference methods, when they work well, we probably shouldn't expect too much for them. But there are a number of places in this industry where there is more challenging chemistry, particularly where enzymes are involved, particularly where metalloenzymes are involved, potentially other mechanisms which involve photo effects. There are a number of cases where we do think that the application of the techniques could be genuinely interesting. Before I sort of pull that together, I just want to highlight one other thing. I mentioned earlier that we're really trying to solve the problem end-to-end and pull all the correct tools together. And that means also looking towards where there are additional feature sets which may not be calculated on a quantum device in future, So something like this. And we did explore this briefly because actually our data set was a small data set containing mostly fairly small molecules, which were mostly sort of fairly planar. And this becomes a challenge when looking at the local electronic structure for such properties when you look at bigger molecules, and that's because steric effects play a role. So what we tried to do is also include steric effects in a bigger data set of bigger molecules and see where we got to. And that's kind of our final ingredient here. We're able to essentially recover some of the performance that we lose due to steric effects by throwing those into the data-driven pipeline along with everything else. Okay, I've just got 2 more slides because I think I'm down to the last few minutes. So summary is that we do think this end-to-end pipeline has value in many different places. This is really a first exploration for us in the consumer product space. And we found a bunch of interesting areas to pursue in greater detail. In fact, our team is beginning to look at the space of metalloenzymes, and our lead quantum chemist is actually looking at applying QMMM techniques so that overall we will have a kind of a QMMM embedding where we can extract features from the core of a problem. And I also want to acknowledge the team from Capgemini and Unilever who have really driven this work forward and made it happen. But I also wanted to leave you with just a brief overview of some of the other areas where we're applying these approaches and where the use cases are a little bit more mature as well. So on the left-hand side, we have a number of things that we are working on and that we are building out. So one is around exploring robustness of the pipeline. We think there is a robustness that, in fact, we already see in some of our examples, a robustness due to the fact that we're using machine learning downstream in the pipeline. That means that we can tolerate certain errors to some extent. But there are a number of challenges in applying this pipeline to different problems. So, for example, so far, many of our problems focus on a common center that allows us to compare between series of similar chemistries. We'd like to expand this beyond that. And on the right-hand side, you can see a few of the things that we're doing. So we are working with DARPA on metal organic frameworks for carbon capture and storage. And this is an interesting challenge, again, where you see the sort of interplay between quantum and classical features. So obviously we have metal sites where there's binding of carbon dioxide, but we know, for example, the size of the pores in the material also drive the properties such as the level of carbon uptake, which are possible. Battery chemistry is another interesting area, in particular some of the degradation mechanisms which take place there. That's an area which Julian mentioned this morning. And I also just want to give a quick plug as well on the right-hand side for the work which Marek has been doing. I think he's in the audience somewhere. Yep. On kind of actually reducing circuit depth for some of the things that we're trying to do in this space, and that's work that we're doing in collaboration with IBM. Finally, on the bottom right-hand side, also linking to this body of work is custom error mitigation techniques, and that's work that we are doing with our colleagues in Cambridge Consultants, and James Cruz will be on a panel on these topics tomorrow, so another thing to look out for. And with that, thank you for your attention, and I'll close.
Thank you. Is there any question?
Hello, thank you very much. You talked about like bond critical points. So what do you think is the advantage over doing it on a quantum computer to, let's say, do a beta analysis, which is a quite standard analysis for doing bond critical points, ring critical points, cage critical points?
Yeah, so in this example, there, I don't think for sort of this ESTR example there is any advantage at all. I think when we go to sort of tougher problems, I think where there's a multi-reference character, we think essentially extracting similar features from bond critical points, in situations where you need a multi-reference method, that's where it really matters. So I was trying to be upfront and get that in before.
So because you didn't mention any multi-reference or strong correlation in your talk at all, but the problems that you're calling up, like the food degradation problems and so on, and many problems in drug design, are just like by not by design, but basically they're mainly or fast even nearly all of them like weakly correlated problems, so no multi-reference problems. So where's the connection between the use case that you are showing and the methods that you're saying that will not give an advantage for weakly correlated systems?
Yeah, I think I put that on a slide a few slides back, actually, to try and sort of emphasize that it's a step on the journey, right? We have to find the areas where there is interest in some cases, actually moving to quantum simulation at all from chem informatics, because actually we need there to be more quantum simulation going on for people to care about applying quantum computers to quantum simulation. And then from within that, find those tougher challenges. So I think my experience so far is that those challenges are obviously they are more sparsely distributed across those sectors, but I think there are a few where we are beginning to sort of move on to those, and this project has actually sort of led us onto some of those where the same ideas we're wanting to apply to tougher chemistries. But you are completely right to call it out. I had hoped that I had sort of put that out there at the beginning, but it's something we should all be very aware of working in this space, so it's a very good point.
Thank you very much.
Is there any other question? Just a quick question, maybe I missed it, but which model do you use to predict which type of machine learning?
Oh, yeah, sorry. In some senses, in these smaller problems, the machine learning is not the most complex part. So actually, in this case, we have a bunch of correlated features. We're looking at partial least squares models, but actually, as long as we are validating the machine learning models well, given that we have small data sets, which is just, kind of machine learning 101, our findings are not overly sensitive to the machine learning model. These are still relatively small sets of, of features, so sort of a couple of tens or so in this context. So actually, the most important thing is that we're really validating and that we can convince that that those correlations we're drawing on are genuine. So partial least squares is good because it's easy to keep a handle on the complexity of the machine learning model that you're building, but I wouldn't be too anchored on that as a sort of only solution. I think as we build complexity in what we can capture, then we'll also want to build complexity in the ML that lies downstream as well.